Okay, great. Thank you. I'm going to try to draw together some of the things that we've been talking about this morning about photovoltaics and about fuel, and really to enable human progress. I share Dan's outlook and sort of aspiration. And this view of the Earth, I think, like Steve Chu's, tells us something about the fragility. You see the thinness of the atmosphere and the finite size of the Earth, but you can also see how sunlight broadly illuminates the entire planet. As Dan said, it doesn't discriminate, it doesn't shine only on the rich countries. So in 2015, when the world's leaders met in Paris for the COP21 climate treaty, this guy from Redmond, Washington, published a very interesting white paper entitled Energy Innovation. And more recently, he's also putting his own money where his mouth is to actually develop a private sector investment in clean energy innovation called Breakthrough Energy Ventures. And the reason is sort of captured in this chart. And this is a plot, apologize for the small type here. It's grams of CO2 per kilowatt hour of energy. So it's essentially the carbon intensity of energy. And this tells you what the carbon intensity of our energy system globally is. And the units aren't so important, but what is important is to see where we have to go in order to meet the goals of the COP21 climate treaty. We over the next 30 years, need to drive the carbon intensity of energy essentially to zero. But the challenge is even more daunting than that, I have to say, somewhat soberly. If you look at this, this is the dotted line these represent the 2 degree, 4 degree, and 6 degree warming scenarios. Of course, we want to be on this one, the 2 degree, if at all possible. That's what the COP21 delegates, the world's leaders, essentially signed us up for. However, the new infrastructure, so we have this capitalized infrastructure that we have to use for some period of time before its capital is all amortized. As we build new infrastructure, the carbon intensity of the new infrastructure essentially has to go to zero almost immediately. So this is just a Sisyphean, an impossible task. So we're going to need negative emissions. That means we're going to need to, in addition to decarbonizing as quickly as possible, electrifying everything that we possibly can in our infrastructure and society, we're going to have to, because this is going to be very likely to not happen, we're going to have tools that allow us to convert carbon dioxide to something useful. So here's where we are now. So this is a challenge for you and your generation. Okay, so when I was your age, this was the state of the US solar industry. And in fact, the US solar industry was the world solar industry because only a few megawatts of solar panels had been produced. In 1977, I was a senior in high school, like you. I grew up in Pennsylvania, and during the cold winter of 1977, our school, you may remember that was a time when the Arab countries embargoed oil to the developed countries in the world, and there were fuel shortages, and my school shut down for a period of about 3 weeks that winter, and that made a big impression on me that somehow these forces dictating our energy supply from far away in the world could have a big impact on my life as well. So I vowed then, if I ever had a chance in my life to do something about it, to address energy. So I encourage you to think about things that are meaningful to you in your life and see if you can pursue them. So what's interesting about the photovoltaics industry, and the reason I think it gives me tremendous inspiration, is that it is a Moore's Law energy technology. We all know about Moore's Law, which is the scaling relationship by which the costs were reduced and per bit of information technology. that is an exponential scaling law with time. In other words, the costs decrease exponentially, and the volume of bits produced in integrated circuits increased exponentially. So what we can see here is that this is Suzanne showed it on a semi-log plot, so you saw a straight line, but it's more dramatic, I think, if you just see this exponential drop and exponential rise in manufacturing capacity. And so this was unimaginable when I was your age. This was like a figment of our imagination in the future that this would ever happen. Are all energy technologies like this? Well, consider that shortly after I graduated from high school, the price of oil was about $32 a barrel on the world market. The price of oil yesterday was $56 a barrel. So we didn't see an exponential decrease in the price of oil. So there's something about these Moore's Law technologies. And like Dan said, if you can manufacture many units, you can get much better at it. And these kinds of things occur. In fact, many manufactured goods follow these experience curves. So what about the world's solar technology today? It's the world's largest optoelectronics industry. In fact, the photovoltaics market just surpassed the display market in terms of turnover in the world. It's growing faster. About 90% of this is silicon technology. There's some thin film, as Suzanne mentioned. About 75 gigawatts of capacity. Mid-20s to 26% record efficiency. Commercial cells of the order of 19 to 21%. Modules about 2% less than that. And the costs are still going down. In fact, in the last year, if you haven't looked at the price of a solar module recently, your information is out of date. The price in the last year went down by a factor of 2. Can you think of any other energy generation source for which in the last year the price went down by a factor of 2? And it's going to continue. And so now it's 35 cents a peak watt. But there is a problem. And that is that the electrons produced by renewable sources aren't always available when you want them. We depend, in fact, you depend on the idea that the electrons will be there when you plug your appliances into the wall. There's some, this black line is over the day. The energy use, so we tend to use energy here. In the middle of the day, and in fact, mostly at the late part of the day, we have a peak in energy use when people come home from work. And wind and solar are somewhat counter-cyclical, but they're both intermittent. Solar is predictably intermittent, and of course doesn't produce anything at night. Okay, how about this? We also have seasonal variability. In fact, this is here data for Gothenburg, Sweden. And you can see from here the depth of winter to the summer, there's essentially a factor of 10 difference in the solar irradiance. And this factor of 10 means that we would, to have the constant energy generation supply, we'd have to have 10 times more solar panels in the winter than in the summer to produce the same dispatchable energy supply. And so that also is over this time frame, half a year, is a time that's too long for us to essentially store energy, probably in electricity storage in batteries. So we need some other source. So batteries could probably manage this, or pumping water could also manage this, but we need solutions for both of these. And what that has done basically is to mean that the effective value of electricity goes down with the more renewable electricity that you put into the grid that has this intermittent character. And these are scenarios for Texas, California, and Germany, showing that when there's a tiny fraction of photovoltaics in the market, the effective price or cost can be somewhere 6 to 10 cents a kilowatt hour. But as you start adding a lot, the value of that photovoltaic electricity goes down tremendously. In fact, in California, there's sometimes in the late spring when close to 100% of our power, about 11 a.m. in the morning, is generated by photovoltaics. And in fact, part of the solar panel system in California has to be curtailed. In other words, stop generating energy because the output is too large. So that means we have a real need for storage. So there are essentially two paths forward that I see. One is to, Suzanne and others talked about the cost declines and talked about the fact that in certain favorable situations, photovoltaics is already a cost-effective form of energy. But if you think about the dispatchability, I actually argue that we're not there yet. That there's still a big challenge. We need to make it even cheaper, less than 3 cents a kilowatt hour, because we have to also pay for this storage in order to make energy dispatchable. And then, as Dan described, this is, of course, the other challenge that has many possible advantages and opportunities. Okay, so how can we make progress in this regard? One way we can do it is to see if we can increase the efficiency. So today's silicon solar panels are about 18 to 20% efficient. So why is it that they are not near the Carnot limit of efficiency? Why is it that they're not 93% efficient? You should be disappointed that they're only 18 to 20% efficient. And the reason is because much of the energy of the photon, this excess energy that's above the energy gap between the ground state and the excited states in the semiconductor, is lost as heat. And in fact, even if I have a photon energy that's exactly equal to the energy gap, I still get a voltage out that's smaller than that. And there are a variety of physical effects that have to do with the balance of energy and entropy in the solar cell. And in fact, there are potential engineering approaches to mitigate these effects. And to go further, we have to essentially appeal to a wise scientist here, Arnold Sommerfeld, who gave us one of our first models of the atom, who opined that thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. This is for the faculty. The second time you understand it, you think you understand it except for, or the second time you go through it, you think you understand it except for 1 or 2 small points. The third time you go through it, you know you don't understand it. By that time, you're so used to it, it doesn't bother you anymore. So in that spirit, we'll conduct our study of thermodynamics. And essentially, I only have one equation. And that equation really is to emphasize the fact that the energy in a solar cell is a type of energy, a generalized form of energy, what's called a Helmholtz free energy, that includes the energy, the energy required to excite electrons from the ground state to the excited state, minus factors that increase the entropy. Paul Alivisatos talked about entropy. And in fact, that's the factor that dictates the voltage. And that's why we end up with a voltage that's smaller than the energy gap in a solar cell. If we could run the solar cell at absolute zero, then T equals 0, and then the free energy, or the voltage, is just equal to the band gap, and that would be great, except we run at finite temperature. And there are effects that have to do with the fact that materials don't have radiative efficiency of 100%. The best solar cells are the ones that glow. The best solar cells are also great light emitters. They're great LEDs and lasers. To the extent that your solar cell doesn't glow, it's less efficient than it should be. There's another loss mechanism that has to do with the change in the number of directions the light goes as it luminesces. And that's a fairly fundamental one that's hard to get over. So the net result is that the voltage is smaller than the band gap and the photon energy resonant with the band gap. You could view the voltage essentially as being the pressure of water induced as we flow a flux of photons, like a fluid, into a bucket. And these entropic loss terms are like leaky points, holes in the bucket. The more I have of these, the smaller is the water level and the pressure, or the lower is the voltage. So if we think about the materials that we would like to make a solar cell, we're going to pick band gaps that have an ideal match to the solar spectrum. And we're going to concentrate on materials that have these characteristics that they literally glow. And so there are certain few privileged semiconductors here that have this characteristic, like this one here, gallium arsenide. So let's pick the highest efficiency. And if we now think about the physics of how a solar cell works, in a silicon solar cell where the cell does not glow, we don't make LEDs out of silicon. In that case, we think about the physics of how the solar cell works in terms of absorbing photons, generating electron hole pairs, and getting them out of the semiconductor and into the wires. In the case of a gallium arsenide solar cell, what we can do is to make a thin film solar cell and put on it a back reflector, and this material that is luminescent, that glows in the infrared, if you could see at that wavelength, means that there's essentially a dense gas of photons inside the semiconductor. The photons come along, they generate an electron hole pair, but the material is so efficient in its radiative efficiency, when the electron and hole recombine, they emit another photon, and that process goes back and forth, 100 times, as much as 100 times. When the radiative efficiency is close to 100% and the reflectance of this back surface is high, I can recycle these photons. I get a dense gas of photons, a dense gas of electrons and holes, and the voltage goes up. That pressure in the line connected to the bucket goes up. And as a result, we can make thin film solar cells that have, and we developed at Alta Devices, a technique for peeling off thin films, like you peel a Post-it note off a pad of Post-its or a piece of paper off a pad. So we can use a relatively expensive substrate, peel off a layer, grow another layer, peel it off, and use that substrate hundreds of times. So this is a single crystal, 28% efficient gallium arsenide solar cell. As you can see, it's flexible. So I'll give it to Bengt, and he can verify that it's flexible. We can also gang these together in series parallel combinations and make flexible modules, so you can get whatever voltage or current you like. And you can see on the backside there's a metal film, and that's acting as a mirror, and it's also, the semiconductor is a brittle material, and it would fall apart and break if it weren't held in compression carefully. And that compressive stress makes the material very durable. And this recycling of the photons has enabled us to be able to achieve world records that have stood for 5 years for a single junction, one sun flat plate solar cell, for a dual junction cell, also a world record, and for a module, world record as well. So this is a very powerful principle. So, but a little bit about technology development. Paul Alivisatos mentioned this yesterday, and Richard. It takes a while to get from the point. Here's my co-founder, Eli Jablonovich, and I founded the company in 2008 with students. It was lots of fun. We rented a building in Silicon Valley. Eventually, we made some prototypes, record efficiency cells, modules, and so forth. We had to build a lot of machinery. Here's the CEO standing in front of a big machine that makes these materials. And then finally, here, 6 to 7 years later, we're starting to ramp into manufacturing. That means they don't need the professors around as much anymore. But it takes a long time to do this. By the way, somebody asked about electric-powered airplanes, or about powering airplanes with solar cells. This is the wing of an electric-powered airplane. In fact, Alta is now selling to make fully electric-powered unmanned aerial vehicles and roofs for automotive glass for high-end automotive products. But these cells are still expensive. So they're of the order of $10 a watt in a flat plate form. But we need to make them more like 10 cents a watt. If we could make them 10 cents a watt, we could combine them with a silicon solar panel. And this is something that we're doing together with Paul Alivisatos. And to go from $10 a watt to 10 cents a watt, we need to be able to drop the cost per unit area by a factor of 100. That means we need to be able to make only 1% of the flat area be the solar cells. To do that, we need a concentrator of a factor of 100. And as Paul told you yesterday, we have a luminescent solar concentrator that can produce a factor of 100. So this is a tandem combination that produces here not gallium arsenide, but indium gallium phosphide cells, similar sort of process that I described before, to enable modules with greater than 30% efficiency. And as another very interesting aspect about the tandem that will come up in a minute is that the tandem also creates a higher voltage. And to do things like splitting water, we need a higher voltage than you can get from just a silicon cell by itself. So this shows the cross-section of the waveguide, the absorption spectrum of the indium gallium phosphide solar cells, the absorption spectrum of the quantum dots. They absorb in the blue, they luminesce in the orange, but they luminesce such that they're absorbed in the indium gallium phosphide. The silicon does the work of power conversion from the red to the infrared. So to keep these concentration factor high, we have to make mirrors that reflect just this wavelength for the luminescence photons. And here we've made a mirror that has greater than 99.9% reflectance right at the luminescence wavelength. So it can recycle those photons in the waveguide many, many times. And you can see the reflectance here out of band is only a few percent. So let's talk about fuel for a minute. And so this morning at the coffee break, I saw a number of you were eating the sandwiches. So this isn't a sandwich, it's a jelly donut, but it's maybe similar caloric content. We call that 400 calories. And of course, to a chemist, that's 400 kilocalories. And if you work with MKS units, that's 1.7 megajoules. Now let's compare that with your laptop or your phone battery. So if I were to have unit interconversion, and I could make, say, electricity out of this donut, that's, of course, a big conceit. Grant me that conceit for a moment. Let's compare. I have 460 watt hours. Your laptop battery is about 45 watt hours. So now you can see I would need about 10 laptop batteries. And this illustrates the incredible energy density that we have in chemical fuels. This is why it's very unlikely that any of us will fly across the ocean on an electric-powered airplane, right? Because the energy density in the fuel is so much greater and so much more efficient than in batteries. And as Dan mentioned, artificial photosynthesis takes inspiration from nature, from the way we use the photosystem for making protons and oxygen from water, and using those protons to drive the process of making NADPH and carbohydrates in a leaf. And so in this form, we make an inorganic structure that has all of the same functional elements, but in quite a different form. So one thing that's interesting to see is the energy landscape of the devices that we make in this tandem geometry. This is why the tandem is very important. That 1.23 volts for splitting water, and it's higher for reducing carbon dioxide, is split here between two chromophores in nature. The one that absorbs at 680 nanometers and 700 nanometers. And charges are transferred between these, and so we excite over 2 to get enough potential here to create the proton equivalents that make NADPH from NADP. Similarly, in inorganic structures, the tandem allows us to absorb both the red and the blue parts of the solar spectrum and convert the energy more efficiently, like the tandem I showed you. But they also, importantly, build the voltage, which allows us to span the energy difference between the energy required to oxidize water on one side, on the anode side, and to reduce water to hydrogen on the cathode side. So in order to go forward and make these structures, there are many key components. It involves a rich interplay of materials, chemistry, and device physics. Discovery of photoelectrode materials. We use, in JCAP, the Joint Center for Artificial Photosynthesis, high throughput combinatorial synthesis. And in fact, we have databases that are big enough that we can do machine learning. In fact, so to do machine learning efficiently, you need about 100,000 databases. So on a plate, very much like a microarray plate that's used for drug discovery, we can make a few thousand to 10,000 different combinations of compositions and optimize, for example, the overpotential for the excess potential required to make oxygen and protons from water. To separate the fuel products, we need to have membranes that can separate hydrogen and oxygen, but nonetheless pass ions. So we need membrane separators. So we use things like X-ray light sources at the national laboratories and surface science measurements to look at the catalytic process with spectroscopic tools right at the level of the protons and electrons interacting with the surfaces of catalysts. And we also build devices, devices like the ones that I passed around here. But these devices also have compartments for the electrolytes that instead of attaching wires, as Dan mentioned, we have electrolytes that directly make hydrogen and oxygen, make fuel. So here's an example. Here's a tandem photoabsorber decorated with non-precious metal catalysts like nickel oxide and nickel molybdenum that make hydrogen from water in a stable form that can last for hundreds of hours. The level of patience of the students that did the measurement here, you can see here the students in the lab shining artificial sunlight on an artificial photosynthesis device for making hydrogen from sunlight. So here's the obligatory bubble video. You can see here, if we look closely, you can see bubbles effervescing here. That's the indication here we're making, on the anode side, we're making oxygen, and on the other side, making hydrogen. If you collect the gas, it comes out in a 2-to-1 ratio, which is exactly what it should for, since our reactant source is H2O. So recently, we've been able to go beyond this. Nan was suggesting that maybe we could get to 20% as a community. Recently, we've gotten to an efficiency of 19.3% by carefully aligning the energy band positions in the semiconductors with the energy band positions in the catalyst, and reducing some of the overall reflection losses, some of the engineering things that he talked about. So this operates in acid conditions at 19.3%, but we can also operate very close to neutral pH in essentially pH similar to water with a buffer at 18.5%. So these are, by the way, also records as far as we know. And efficiencies with a membrane to separate the fuel products safely of almost 15%. So I think we can actually look forward. In fact, we've done some analyses that suggest that the solar to hydrogen efficiencies, if you really engineer and optimize these devices, will actually approach the conversion efficiencies for sunlight to electricity in the low 20s%. So that's quite exciting. So this illustrates how rapidly this has gone. In the last 2 years, the efficiency has gone here from a little more than 10% up to almost 20%. So what about doing this at a large scale? We studied in JCAP the concept of developing a 1 gigawatt plant. Suppose you built a one, we can, for example, there are in the world 1 gigawatt utility scale solar plants. But what about a 1 gigawatt solar hydrogen plant? What would that look like? You would need to make photoelectrochemical cells, assemble them into meter squared panels, and this analysis from our JCAP colleagues at Lawrence Berkeley Labs did what's called an energy return on energy invested. It's not a financial payback, but given that there's a corollary between financial investment payback and energy payback, this is an energy payback analysis. So it basically asks, how long does it take, how much energy do you have to invest, and how much energy you get back? So the first thing we wanted to know is the energy return on energy invested greater than 1? In other words, is the payback positive? So the model included a lot of detail. For example, how do you put these panels onto trucks and transport them? And there's a lot of embedded energy in doing all of these operations. Building panels in the field, making a facility, making all the piping and compression and so forth. And it assumed that this was remotely located, say far from a city, so say notionally somewhere between Los Angeles and San Francisco, piping the hydrogen to one of the cities. And if you look at the energy use, or the embedded energy in the panel, so this is energy return and energy invested, so this is energy embedded, most of it is in the energy costs of essentially making a new panel. So essentially the panel itself dominated. That is a good thing. So in the sense that that means that further advances in the engineering efficiency for the panels could significantly reduce the time required for the payback and increase the energy return. So the energy payback time in this analysis for this set of conditions with 10% efficiency in a 10-year lifetime was about 8 years. So today's photovoltaic panels have an energy payback time of about a year. So clearly that's longer, and we need to get that down. The energy return on energy invested was positive, but clearly it needs to be more positive than that before we make large gigawatt scale plants. But significantly, it didn't turn out that the cost was completely disabled or limited by the cost of the piping, the compression, all of the sort of mechanical and civil engineering aspects. If that were the case, then essentially no change in the design or efficiency of our artificial photosynthetic device would have made any difference. So instead, it turned out that the major sensitivity factors in this so-called tornado diagram that help determine whether the energy return on energy invested can be more positive or more negative, they have to do with whether you can make the device more efficient or whether you can make it live longer, and less to do with many of the other sort of balance of systems, the other issues with respect to making a large-scale plant. So, as I mentioned at the beginning, we're going to have a way to convert carbon dioxide. So JCAP is beginning a very ambitious program. It's really just at the beginning to close this cycle. So I should also say that the capture part is not something we're addressing. That's a challenge that your generation is going to have to come up with better solutions for. But the conversion is also very important. And the goal here is to take solar energy, carbon dioxide, and water, and to produce useful fuels, alkanes, alkenes, primary alcohols. These are the components that go into gasoline and ethanol and things that you can use as transportation fuel. So why are we focused on that? Here, if you look at the usage of and the emissions of hydrocarbons, and you can see here, this 10 gigatons a year is overwhelmingly dominated here by fuel combustion. 8.5 of the 10 gigatons is fuel. So that suggests that we need to find some way of converting this back into streams that can match this emissions from fuel combustion. So we need to either go back into fuels, or we need to find ways that we can embed carbon, for example, in building materials, in things like cement and steel, carbon fiber, for example, if we could use recycled carbon and build, say, airframes and automotive chassis out of carbon fiber. That would be that's currently too expensive, but that would be a good way to embed carbon. Sequestration is something we can do, but it has pure cost. We don't get any financial payback. So the good thing about these is that these are actually things that have greater or lesser value, but they have a financial payback. So as his last act as Energy Secretary, Ernest Moniz, who followed Steve Chu, commissioned a report to study this problem of how would we quickly bring down and capture, say, a gigaton of CO2. How would we enable pathways for negative emissions, either by air capture or concentrated sources? And this is a complicated wiring diagram, and I'm not going to go through it completely. There are many different capture processes, biological, chemical, mineralogical, making transformations as you embed CO2 in rock and letting it undergo transformations. All of these are possible options. And this is a rich and very important research field for the future. So if we start with conversion processes, there are essentially 4 processes. Dan talked about this method and about this method. So these all have advantages and disadvantages. So currently the chemical industry today does things mostly using heat, but you have to build big plants, as we talked about before. These processes are scalable. We can make things that look like photovoltaic panels and make scalable solutions. And so this maybe lies somewhere in between. So in JCAP, we're working on these 2, electrocatalysis and photocatalysis, because they operate close to room temperature and they can operate under mild conditions, near neutral pH and so forth. So for non-biological catalysts, we work with metals, and at the moment, transition metals, the best one is copper. The best one doesn't produce a single product. It produces, for example, methane. It also produces a little bit of methanol. But for example, if I wanted to make a liquid fuel, I'd like to produce much more methanol. Here I have maybe an order of magnitude less at a given voltage methanol than methane. To adjust the product distribution requires going in and changing the atomic scale structure and engineering of this surface. We can do this, for example, by making functional catalyst surfaces where we present controlled surfaces that can change the product distribution. But this is still a very big challenge. Many of these products are linked in their rates of production on all these different metals. Copper is the one that makes many products that go beyond carbon monoxide. I'll just leave you with one concept, which is an exciting direction. By combining molecular catalysts, for example, nitrogen functionalized aryl pyridinium molecules, and condensing them on a surface, we've been able to take something, a structure like copper, which produces mostly methane and hydrogen, and produce 80% liquid fuel products, or C2 products, ethylene, which is a gas, and then ethanol and propanol, which are liquids. So this illustrates the power of molecular frontiers to engineer this process. And this 80%, now we're about 10% hydrogen in a water environment, which is quite spectacular given that most of the electrolyte volume is water. But now you can see we're achieving pretty good control over selectivity of these C2 products, very useful. So that allows us to envision a landscape that contains ways of taking carbon dioxide from fixed sources or capture and bringing together this with transformation methods like electro and photocatalytic routes to produce hydrogen in fuel cells or to produce liquid fuels that are used for aviation and long-haul transportation, driven by renewable sources that will span this intermittency and give us a secure and sustainable energy future. So I'll just stop here with wise words from another philosopher. Thomas Edison, the famous American inventor, was the founder of General Electric. And he, in a very interesting conversation with Henry Ford and Harvey Firestone, of course, people that spawned the birth of the automotive age in the United States, and of course, all the fuel combustion that we're currently contending with. Edison opines, we're like tenant farmers, chopping down the fence around our house for fuel when we should be using nature's inexhaustible sources of energy, sun, wind, and tide. This is in 1931. I'd put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until all the oil and coal runs out before we tackle that. And I hope so too.